Buongiorno a tutti. È un piacere darvi il benvenuto alla sesta edizione della Christmas Lecture dell'Università del Piemonte Orientale, ormai diventata una tradizione, una consuetudine dell'Ateneo che si ripete prima delle festività di fine anno. Porto i saluti del magnifico rettore che non ha potuto partecipare, intervenire, come da consuetudine, perché è impegnato in altre attività istituzionali. Mi presento, sono Leonardo Marchese, il direttore del Dipartimento di Scienze e Innovazione Tecnologica dell'Università del Piemonte Orientale e da questo Dipartimento stiamo coordinando insieme all'Ufficio Comunicazione dell'Ateneo, che ringrazio per il supporto fornito nell'organizzazione dell'evento. Qualche parola su questa conferenza, per la quale abbiamo preso spunto dalle famose Christmas Lecture della Royal Institution di Londra, alcuni di voi la conosceranno senz'altro. La Christmas Lecture hanno una lunghissima tradizione, iniziata, pensate, da Michael Faraday nel 1825, quasi 200 anni di storia caratterizzata da scoperte scientifiche che hanno determinato il nostro stile di vita. Molte scoperte e molti scienziati famosi sono passati proprio dalla Royal Institution, dove, oltre alle attività di ricerca all'avanguardia, è iniziata una ricca attività di divulgazione scientifica per la quale gli inglesi sono veramente eccellenti innovatori. Per capire l'impatto dell'attività di divulgazione, basti pensare che ogni anno le Christmas Lecture vengono trasmesse in prima serata TV dalla BBC subito dopo Natale. Mi piace qui ricordare l'atmosfera che si crea durante una Christmas Lecture nel magnifico teatro della Royal Institution, dove partecipano studenti delle scuole superiori, anche delle scuole medie. È un'atmosfera che ho avuto la fortuna di vivere quasi 30 anni fa, quando frequentavo quell'istituto per attività di ricerca. Vedere l'entusiasmo dei ragazzi e la loro sorpresa durante gli esperimenti in diretta, che ancora oggi vengono tenuti, mi ha sempre toccato e colpito, ed è per questo che ho proposto di creare quell'atmosfera anche per i nostri ragazzi delle scuole superiori. Molti di loro sono ora collegati e quindi saluto cordialmente. Mi rivolgo quindi a voi ragazzi, fiducioso che queste attività di divulgazione sappiano stimolare la vostra fantasia e i vostri interessi verso le scienze. Sono quindi altrettanto fiducioso di vedervi frequentare le nostre aule e i nostri laboratori fra qualche anno nei corsi universitari. Quest'anno le Christmas Lecture avranno come tema il pianeta Terra e l'impatto delle attività umane sul suo equilibrio. Su questo tema abbiamo dedicato la notte dei ricercatori dello scorso anno e in parte lo abbiamo ripreso anche in quella di quest'anno. Lasciatemi dire che il nostro Ateneo ha fondato un centro interdipartimentale sulla sostenibilità e ha recentemente chiesto l'istituzione di una laurea triennale che sarà una sorta di unicum nel panorama nazionale, che prenderà in considerazione non solo gli aspetti scientifici e tecnologici legati all'ambiente che ci circonda, ma anche ne prenderà in considerazione gli aspetti normativi, legislativi, giuridici e quelli naturalmente economici. Anche nella presente conferenza abbiamo voluto affrontare questi temi grazie alla disponibilità del professor Tony Ryan dell'Università di Sheffield in Gran Bretagna, che è un professore di chimica fisica dei materiali polimerici e, fedele alle tradizioni anglosassoni, oltre all'attività di ricercatore che gli hanno permesso di pubblicare oltre 350 articoli scientifici, brevetti, libri, ha anche una intensa attività di divulgazione scientifica per la quale è spesso invitato alla TV e alla radio. Tra queste mi piace ricordare proprio la Christmas Lecture che ha tenuto nel 2002 proprio alla Royal Institution di Londra. Bene, finally, let me say a few words in English to welcome Professor Tony Ryan and his students or collaborators who are connected from England. We are very pleased, Tony, that you accepted our invitation to deliver a Christmas lecture at the University of Eastern Piedmont. It is my personal hope that we can benefit of your program in sustainability research, creating the conditions to collaborate with your center. Our university has recently founded a Center for Sustainability, and one of the missions is to extend the collaboration across Europe and apply for research projects in the new European agenda, which will be mostly dedicated to Green Deal and sustainability. Allow me to say that this event is a clear demonstration that education and culture will never be divided, despite the blind political decision that has been taken to move Great Britain away from Europe. I would like to think that this is a sort of bridge that keeps us tightly connected. Thank you, Tony, for coming, and thank you for your accepting our invitation. The video is yours.
Thank you. Thank you so much. It's really great to be here, i.e. with you virtually. Italy is one of my favorite countries, and I just want to echo, nobody regrets more the political decisions to build barriers between the UK and Europe, especially Italy. And yeah, who knows what's going to happen over the next couple of weeks. However, we will get through it, and we do have things to do with the way we live. And what I want to talk to you about today is an idea of how we might live in the future with respect to plastics, polymers, and I heard the word. So plastics. Well, this picture was on the front cover of the Stylist. It was actually used in Vogue as well, about to become as fashionable as smoking. Well, actually, plastics are not that fashionable anymore. It really is. If you, like me, have been working in the area of plastics and polymers for more than 30 years, introducing yourself as being a professor of plastics is really, really tough, and no one wants to talk to you. And it's 100 years since polymers were acknowledged as existing. Hermann Staudinger received the Nobel Prize in 1953, essentially for a paper that he published in 1920, demonstrating to organic chemists that polymer molecules, large molecules, exist. And his Nobel lecture uses many examples of natural polymers, cellulose from plants, rubber from trees, as well as the more obvious plastic, polystyrene. And his paper, Überpolymerisation, was published in German, in a German journal, demonstrating again the importance of our European scientific and cultural endeavors, as Leonardo highlighted at the beginning. So biopolymers got us started, but then we fell in love with plastics from fossils, from oil, polyethylene, polypropylene, polyvinyl chloride, polystyrene, PET, polyethylene terephthalate, nylon, polyurethane. But now we hate them, even though they're completely embedded in our lives. And what I want to show you is that biopolymers and compostable polymers are not today's answer to the plastics problem, but they may well be the answer to future plastics problems. I'm going to pose the questions: can we make neofossils, new fossils, by making non-degradable plastics, plastics that doesn't degrade in the ground? and to make them from agricultural waste, to make them a byproduct of food production. And if we do that, we can capture carbon from the atmosphere and securely bury it. And I'd always been interested in the environmental fate of plastics because I was keenly involved in making them. But about 5 years ago, Sir David Attenborough turned what was a scientific interest into a cause, into something to campaign about in his program, The Blue Planet. And I recommend, if you've not seen David Attenborough's Blue Planet, you can get it on BBC iPlayer. It's really well worth watching. Magnificent photography and a great explanation of the natural workings of our planet from Sir David. And interestingly, he has come round to the idea that some plastics might actually be useful. But the message you'll hear time and time and time again is that we're polluted by single-use plastic. And this is the issue, the single use. Because plastics are fantastic materials. They're lightweight, they're moldable, you can make them into any shape. But most importantly, they're really, really cheap. But rather than being threatened by single-use plastic, many of us have been saved by single-use plastic. COVID-19 and the pandemic has demonstrated how important plastics are, and particularly single-use plastics are, in the medical field. The face shield, the mask, all of these things require plastic. The gloves are made from nitrile rubber. The gown is made from polypropylene. The apron is made from polyethylene. The face shield is made from PET. We wouldn't have as many people alive today without single-use plastic. And for anyone who's lost a family member to COVID-19, you really do have my deep condolences. What's happened in the world over the past year is an example of the pressure we're putting on the earth. And part of that pressure is through our use of man-made materials. So for plastics, reuse and recycling are both difficult and expensive. It's cheaper and often less energy intensive to make new packaging every time from new polymer. And once you've used a piece of plastic, you throw it away. But there is no away. But disposal by consumers shifts the cost away from the producer of the plastic, the seller of the plastic, and the consumer of the plastic. Consequently, there's 8 billion tons of plastic in the Earth system. And if we keep producing it at the same rate, there'll be 40 billion tons by 2050, by the time you're my age. And of that 8 billion tons, 10 million tons gets into the ocean. Because there's 3 billion tons of litter. Plastic that's just been thrown away and lies on the ground. And there's 5 billion tons in landfills. And some of that also escapes. So there's a great paper called The Production, Use and Fate of All Plastic Ever Made. Basically, it's a collation of all the data. 8,300 million tons of primary production, 2.5 million tons of stock plastic that's circulating. Some of it lasts a long time. Wind turbine blades, parts in cars, but some of it's used only for seconds. And 5 billion tons has been discarded, with nearly 1 billion tons having been incinerated. But look at the small number that gets recycled and gets made into secondary products. And that's something we have to improve now. Because the annual production of plastic that's risen over the last 70 years to now be the equal of the mass of all the people alive today. So 300 million tons, more than 300 million tons of plastic is produced every year. But it only uses 5% of the oil and gas, the fossil carbon we dig out of the ground. And what does 8 billion tons of plastic look like? Well, if it was in a big piece, it would be 8 million cubic meters. That's 2 kilometers by 2 kilometers by 2 kilometers high cube. But if it was cling film, the wrap that you use in the kitchen, that's 13.2 microns thick, a roll would go back to Pluto, to the Earth, and back again 140 times. Or if we made it into kitchen cling film, it would cover the surface of the Earth, 510 million square kilometers, with about 25% to spare. And they're frightening statistics in themselves, right? Pluto and back 140 times, cover the entire surface of the Earth. But the most frightening statistic, the most frightening calculation I made was that in 50 years, we produce more plastic than all the people that ever lived. So since Homo sapiens walked on the face of the Earth, the best estimate is that there's been 107 billion people at an average mass of 62 kilos each. Okay, I'm a little more than that. But more plastic in 50 years than all the people that ever lived. But we hear all sorts of nonsense about plastic. So my favorite newspaper is The Guardian. It's a liberal newspaper with a small L. And it produced this article, 1 million bottles a minute, the world's plastics binge as dangerous as climate change. Bullshit. Complete nonsense. The article talks about plastic bottles, PET bottles, water bottles. 500 billion a year next year. Can't recycle them fast enough. And the picture below shows the problem. You have to separate the colours in order to give value to the plastic. It's labour-intensive work. And we ship plastic, waste plastic, all over the world. But this is a convenient truth. This is something you can see. Because only 5% of oil and gas is turned into plastic. 87% is burned to make carbon dioxide. And that produces global warming. And the burning of oil and gas also creates tiny particles of soot, and they cause respiratory diseases. actually make people more vulnerable to COVID. And this week in London, a judge put on the death certificate of a young girl that she died because of air pollution caused by the combustion of fossil fuels. So it's a global problem, and the local problem is burning. And here's the inconvenient truth of global warming. So I love this graph because it starts when I was born and comes up to today. It's the atmospheric concentration of carbon dioxide at the Mauna Loa Observatory in Hawaii, and it measures carbon dioxide as a concentration in parts per million in the atmosphere. Before the Industrial Revolution, the level was 280 parts per million. When I was born in 1962, it was 320 parts per million. When my PhD students were born, who were in their mid-20s, it was 360 parts per million. And today, it's 420 parts per million. The Earth System Research Laboratory draws the black line and the red line. The black line's the annual average. The red line shows you how the carbon dioxide level in the Northern Hemisphere varies between summer and winter. Summer, when there's more photosynthesis. Winter, when there's less photosynthesis. And I've put on this blue line to show you that the level of carbon dioxide in the atmosphere is accelerating and continues to accelerate. And this is the inconvenient truth. So the Paris climate change talks that I attended got an agreement to reduce carbon dioxide, to cut emissions down. Because carbon dioxide emissions have been associated with a temperature rise. And the climate change talks had a temperature target. And what the climate change talks said was that we would defossilize. Actually, they said decarbonize, but they should have said defossilize. We will defossilize our emissions to cut carbon dioxide and eventually get to negative emissions, where we take carbon dioxide out of the atmosphere. So this is what the world agreed to do, okay? And then up here, this is what's happening. There's no slowing down in the production of energy, and the growth in renewable energy, in fossil-free energy, only adds to our consumption. And the only fossil fuel where we've slowed down our consumption is coal. We're actually growing the consumption, the burning of oil and gas all the time. So how can we decarbonize the energy system? Well, we hear lots about solar power, wind power, and hydropower, and its conversion into electricity. I took delivery of an electric car earlier this week to move away, my personal move away from fossil fuels. But if you have excess, lots of nuclear energy, you can actually do some chemistry. You can take carbon dioxide, nitrogen, water, split them to make oxygen. strip out the hydrogen from water to store hydrogen that can be then used as a fuel, to make ammonia as fertilizer for agriculture, and even to make synthetic fuels. And then all the things we need, chemicals and materials, fuels, we can get from renewable energy and biomass. What we have to stop doing is emitting carbon dioxide and find a way to bury it. So there are all sorts of technologies. This guy, the UK's idiot in chief, the worst prime minister we've ever seen, announced the 10-point green plan with lots of job creation only a month ago. It had all of these technologies in it. Negative emission technologies, technologies to take carbon dioxide out of the air. Planting trees. Making biochar, basically charcoal that you can bury. Biomass energy with carbon capture and storage, or carbon capture and utilization. Taking carbon dioxide directly from the air and storing the carbon dioxide underground. Growing plants in the sea to enhance carbon capture in the coastlines, and actually fertilizing the ocean so that carbon capture is more efficient in the upper ocean. These technologies, these carbon capture and burial technologies, are not demonstrated at scale. They're more like fairy stories. And agriculture, forestry, and other land use. Well, if we plant enough trees, we could sink 4 billion tons of carbon dioxide a year. If we allowed wetlands to be wet and make peat, we could sequester 4 gigatons of carbon dioxide a year. And if we changed the way we did farming, we could sequester a couple of 2 gigatons of carbon dioxide a year. So using the land better does present opportunities to capture carbon dioxide from the atmosphere. And what all of these technologies have in common is the same piece of chemistry. They use photosynthesis. Photosynthesis, biology, is the ultimate in carbon capture technology. So what happens in a leaf is that it's the ultimate in carbon capture technology. So what happens in a leaf is that it's the ultimate in carbon capture technology. Okay, you heard it again then. What happens in a leaf is the ultimate in carbon capture technology. Solar energy comes in to the leaf. There are catalysts in the leaf that split water into oxygen and reactive hydrogen. And that's called the light reaction, because it takes its energy from the sun. And then that solar energy is embedded in the reactivity of the hydrogen. And then the hydrogen reacts with carbon dioxide to make carbohydrate, organic molecules, and water. And in doing so, puts oxygen into the atmosphere and takes carbon dioxide out of the atmosphere and builds biomass. So On the surface of the earth and in the upper part of the sea, 250 billion tons of biomass is produced every year. That's just by photosynthesis. Agriculture, farming, produces 25 billion tons of biomass a year. And of that 25 billion tons, that 25 gigatons of biomass, 5 gigatons, 5 billion tons is food. And of that food, more than half, 2.6 gigatons, 2.6 billion tons are cereals, pasta, cornflakes, potatoes. $5 billion tons of food, 25 billion tons of agricultural biomass. Therefore, there's 20 billion tons per year of photosynthesis that's wasted. So, how much of a plant is edible? Well, we call that the harvest index, the edible mass of the plant divided by the total above ground mass of the plant. And elite cereal crops, about 40% of the mass is the grain and 60% of the mass is the rest of the plant, the leaves and the stalks. And that means that 60% of the carbon dioxide that was fixed by photosynthesis is wasted. And you can understand the harvest index if you think about tomato plants. You can see how much of the tomatoes are edible compared with the leaves and stalks. And the production of cereals over the last decade has continued to grow. And we currently produce more than enough cereal to feed the approaching 8 billion people on the planet. So food production isn't particularly a pressure. And every hectare of cereal growing land produces 8 tons of wheat and 12 tons of straw. And the straw is also mainly carbohydrate. But what happens to that straw? Well, it's biodegradable. It's left to rot on the field, where it causes carbon dioxide emissions. Or it's ploughed in as fertilizer, where it causes carbon dioxide emissions. Or it's burned in situ, or collected for fuel in some countries, where it causes carbon dioxide emissions. So the agricultural waste started the year as carbon dioxide in the atmosphere, passes through the crop, and ends the year as carbon dioxide in the atmosphere. The 40% that was food started the year as carbon dioxide in the atmosphere, was turned into food that we ate, and then becomes carbon dioxide again as we breathe it out. Now, if you change agriculture so that you're not ploughing the land and losing carbon, but drilling the land to plant seeds and using a cover crop, then rather than losing carbon from the soil, you can put carbon back into the soil. You can actually put about 2 tons of carbon per hectare back into the soil again, just by changing the way you do the farming. And in a big field, you get 8 tons of wheat, 12 tons of straw. That's a carbon budget of 30 tons per hectare. 10 are turned over in respiration. That's the plant breathing. 20 are fixed, carbon dioxide being turned into carbohydrate, and 8 in food, 12 in waste. Of the carbon left on the field in the waste, 2 can get returned to the soil pool and 10 goes back to the atmosphere. And it's that 10 going back to the atmosphere that I want to tap into. So the new plastics economy that the Ellen MacArthur Foundation's pushing recycles all plastic. Plastic goes round in a loop. You design and produce plastic, you use it, you reuse some things, like a lunchbox, for example. And after it's used, it goes round the cycle in a circular economy of plastic and is designed and made into new articles that go round and round the cycle. And what the Ellen MacArthur Foundation wants to do is decouple plastics from fossil feedstocks to make renewably resourced plastic. And I kind of agree with that. I just think the timing's wrong. And actually, we don't want this renewably resourced plastic to decompose. Because if it's come from plants, it's fixed carbon. It's turned it into a solid. But people want to do the right thing. They want to behave properly. That's why you get greenwash, people painting their products green. So Dasani is the water brand of the Coca-Cola company. And basically, it's water that comes from the tap. It's city water that's put into bottles with a label. And the label has a plant on it because the bottle comes from plants. It's actually only 30% plant, and it says that on the bottle, and we'll come to that later. And we've just done a massive experiment on compostable plastics. Will bioplastics, things that are labeled as compostable, decompose in the ground? Well, the answer is they don't decompose in a home compost heap. You have to do it in an industrial composter. And if they do decompose, it's back to water and carbon dioxide. Therefore, you've not achieved anything in terms of capturing carbon. But we are working on a plastic circular economy because it's absolutely essential today. So what about bioplastic? You can go buy a bioplastic bottle of water today and think you're doing a good thing. And it has a label on saying plant bottle. And if you read a bit more what it says on the label, it says that the plant bottle is 30% made from plants and 100% recyclable. The 100% recyclable is a good thing. It's the same plastic as from a conventional bottle. And the 30% made from plants, is that a good thing? To work that out, you need to do something called a life cycle analysis. So Louis Chen, Riley Pelton and Tim Smith have published this great life cycle analysis of fossil and bio-based PET bottles. And what you have to do is you have to draw a picture, you have to draw a box of what happens. So PET is made from terephthalic acid and ethylene glycol. And if it's made from fossil sources, then you get paraxylene from the chemical plant, from the oil distillation, and then that's turned into terephthalic acid by oxidation. Or you get ethylene that's oxidized to ethylene oxide to ethylene glycol, and then these two are reacted to make PET that's then made into bottle PET, bottle grade PET, and then a PET bottle. And if you want to make PET from biomass, you have to collect plant matter, turn it into isobutanol, then turn by hydrolysis, fermentation, then convert that into paraxylene, and then you're into terephthalic acid, or biomass, ferment into ethanol, dehydrate to ethylene, and then it's the same process. So this area in green is what I call the biomass burden. You have to put extra energy in to convert the biomass into paraxylene and ethylene to start making the plastic. And if this biomass burden is using fossil fuel energy, then you're having to burn oil, to make plastic. And all of these graphs basically show the environmental impact. So if we look at the amount of carbon dioxide produced, and we're going to use fossil-based terephthalic acid, wood-based terephthalic acid, and cereal-based terephthalic acid. And then ethylene glycol from fossils, ethylene glycol from cereal, ethylene glycol from a specifically grown biomass product, switchgrass, and ethylene glycol from straw. Fossil terephthalic acid, fossil ethylene glycol has the lowest CO2 emissions. No other combination is lower. In terms of sulfur in the atmosphere, particulates, smog, fossil is always the lowest. It doesn't matter which indicator you use, bio-based PET is always worse than fossil PET, and it needs the avoided impacts to get anywhere close. And what are the avoided impacts? Well, if you use wood-based terephthalic acid, you don't burn the wood, so you don't have the particulates. And if you don't burn the wood, then you get some benefit in terms of CO2 emissions because you've not released that CO2. So not burning the wood, not burning the agricultural waste can bring that polymer that's made from biosources closer to the fossil source. So then we have to ask the question, should we burn more oil to make bioplastic? Obviously not. How much oil goes into plastic? About 5%, 300 megatons a year. So should we start to make plastic from renewable sources? Well, yes, but it depends on the life cycle analysis. And we should only really do it at scale when we've completely decarbonized the energy system. And then we could use these avoided emissions to sequester carbon dioxide from the atmosphere. And you can make every current polymer, every current plastic can be made from bio feedstocks. There's no new science here, it's only scale. In fact, there's a Brazilian company, the name's kind of easy to get, Braskem, and Braskem make what they call green polyethylene. And they make green polyethylene by growing sugarcane. And then that sugarcane's made into ethanol. And then the ethanol is dehydrated into ethylene and made into polyethylene. And then they call this green polyethylene, and that can make polyethylene products, milk bottles, all the things you're used to. Consumers can choose to buy green products. Green polyethylene is 100% recyclable. Of course it is. It's polyethylene. And what's happened is starch and cellulose have been converted into glucose. Oops. Glucose has been fermented to make ethanol and carbon dioxide. And then the ethanol has been dehydrated to make ethene, ethylene, and water, and then polymerized to make polyethylene. Each of these steps has an energy input and an associated production of carbon dioxide. Now, because the energy input often comes from electricity, as we change the electricity system, as we have more windmills or more solar panels, the intensity of the grid, the carbon intensity of the grid comes down. So for every kilowatt hour of energy produced in 2018 in Europe, there was nearly 200 grams of carbon dioxide emitted. That's falling. I can look up on a daily basis the carbon intensity of the electricity in the UK. Yesterday was windy. It was actually down to 70 grams of carbon dioxide per kilowatt hour. So I felt very smug yesterday charging my electric car with low carbon energy from wind. So if you make plastics using energy, as the carbon grid intensity falls, so does the amount of carbon dioxide produced per kilogram of polymer. And because of the avoided emissions, because you're not burning or composting or rotting or ploughing into the soil, the biomass, the biopolymer at some point falls below the fossil polymer. And we've done those calculations. And we've done them for fossil PET, for polyethylene, for polystyrene, for bio-PET, for a polyester that replaces polyethylene that's biodegradable but made from fossil plastic, and for polylactic acid, a bio-based and degradable polymer. So we're going to compare fossil-based non-degradable polymers with bio-based non-degradable polymers, bio-based degradable polymers, and fossil-based degradable polymers. And what's interesting is that every polymer, because of the way it's made, has different contributions of electricity and energy as heat and natural resources in its production. So we can take advantages of these differences. Look how LDPE has much more heat in than fossil PET. But bio-PET, because you have to do the fermentation, takes a lot more heat and a lot more electricity. So the British government predicts the energy intensity, the emissions. So the carbon dioxide per kilowatt hour for UK electricity. And this is the forecast. And actually, we're not quite doing double the forecast because we're building so many wind turbines. But for electricity in the UK, we're doing really, really well. So we're reducing the carbon dioxide per unit of energy. And if we put those numbers into the carbon dioxide per kilogram of polymer, you see that bio-PET falls, but it never gets close to fossil PET. But biopolylactic acid, that's often used to replace polystyrene in food packaging, that actually has a crossover in 2031. So in 2031, it makes sense to use biopolylactic acid to replace polystyrene. It doesn't make sense today. And you need to work out what you're going to do with the polylactic acid afterwards, because you don't want to return that carbon dioxide to the atmosphere. And if you double the rate of energy intensity, carbon intensity of energy, both for electricity and heat, you can actually get bio-PET to approach fossil PET. It makes sense to replace polystyrene with polylactic acid in a couple of years. But nothing gets close to fossil polyethylene. We're currently doing the calculations for biopolyethylene, and I can't show you those today, but they're going to look like bio-PLA. And at some point, there will be a crossover when it will make sense to make polyethylene from biomass and not from natural gas. So I've shown you how, as you change the energy system, biopolymers start to make sense. We use 300 million tons a year of plastic. That's 0.3 of a gigaton per year. There's 20 gigatons of agricultural waste. So if we use defossilized energy to turn agricultural waste into plastic, how much carbon could we sequester? And the answer is, we could sequester about 1 gigaton of carbon dioxide per year, every year, for as long as we consume plastic. And actually, as plastic consumption grows, we could sequester 2 gigatons of carbon dioxide every year. Suck carbon dioxide out of the atmosphere. Plastic could be carbon negative. And the way we do that is that sunshine and carbon dioxide would go into crops. Those crops can be made into biodegradable plastic, and that kind of brings the carbon back. Carbon, nitrogen, and phosphorus go into our food. That carbon, nitrogen, and phosphorus goes into people. Some of it goes back through the sewage system, and we can actually use our poo and wee as fertilizer and put nitrogen and phosphorus back into the crops. And then the crop waste we turn into plastic, either plastic goods or plastic packaging. And that goes via people. And then when we've finished with the packaging or those goods, we can bury that plastic and make new fossils. So the carbon dioxide passes through crops and food to make plastic that then gets buried at a rate of a gigaton per year. And a completely different story is how we recirculate nitrogen and phosphorus through this crop, food, people, fertilizer cycle. We get a gigaton of linear carbon. And I think if we did that, we'd be able to go circular on most of the nitrogen and phosphorus as well. So there's 30 gigatons of carbon goes in as agriculture, and 5 gigatons is all that's used in food. And how would you do it? Well, you build farms on the kilometre length scale, And the food and the agricultural waste is produced on the kilometre length scale at the rate of 20 gigatons per year. You'd want to have fermenters, maybe not on every farm, maybe at a 10-kilometre scale, and get them to produce a gigaton of ethanol per year. And you wouldn't separate the ethanol from the water at the farm scale. You'd want to benefit from economies of scale and do that at the 100-kilometre length scale, and then deliver ethanol to chemical plants at the 1,000-kilometre length scale, where you do the dehydration of ethanol to ethylene and polymerization to make polyethylene and make 500 million tons of polyethylene a year. And then with the ethylene, you could use other chemistry to build up all of the things that we used to use in our everyday life. So toothpaste, shampoo, clothing. The capital investments scale with distance and carbon intensity. And why is burying plastic better than burying carbon dioxide? Well, that's obvious. Plastics are solid. Bioenergy with carbon capture and storage tries to bury gas carbon dioxide. Try burying a solid rather than burying a gas. It's much, much easier and far less likely to leak. So what does a neofossil have to do? Well, it has to lock up carbon and safely go down a hole, not degrade back to carbon dioxide and water. So you might not want to use polylactic acid, PLA. PET will really work, and actually composites, thermosets look great because they will be buried forever. Similarly, biopolyethylene, that's why we're doing that life cycle analysis. And we're doing it to work out when it will make sense. So for the second century of plastics, we need to make sure that we're not distracted by this convenient truth of plastics waste. We need to understand the benefits of plastic we want to maintain, and we need to maintain them in a circular economy for now. Then, balancing health and environmental costs, we should work out when we can use plastics to sequester carbon dioxide and return to single-use plastic again, where we use the plastic and then bury it. And in doing so, put carbon back under the ground in a highly refined form. And then what we're doing is making fossils from plastic and not plastic from fossils. And we will be able to hashtag put it back in the ground. Thank you very much for listening.
Well, thank you, Tony. Thank you for this really exciting and inspiring lecture. So I think that we might use an extra time for some question if there are people connect. Oh, just by the way, there are hundreds of people connected. We are more than 400 people.
Wow.
But much more because some of these connections are entire classroom. So there are hundreds of students. So I would like to thank especially their teacher, the teachers that contribute to stay with us, and so they collaborate with us since long. And so for this reason, our university is growing in this territory just because of their efforts. So
wow.
Thank you to all the teachers that are connected today. If they unfortunately, we cannot keep the chat open because there are too many people around. But in the connected through Zoom, there are colleagues that I invite to give their to ask some curiosity. Or is there anyone? If someone want to talk, they have to switch on the microphone. Ah, okay, Enrico. You know, Enrico is in his classroom. You see, Enrico, why? Hi. You can.
Yeah. Hi, Tony. Thank you very much for your lecture. Hi. We are all around here in the lab, but we moved to a classroom to follow your presentation, and it's very nice. Actually, we have to come back to the lab, but there are two questions that maybe we can pose rapidly. The first one is there a way to, let's say, stabilize these waste polymers for the burying? I mean, for instance, taking out hydrogen with a partial pyrolysis, if it is a way. And the other one is the low density of plastics a drawback for the storage with respect to oil?
Okay, so let me deal with the second question first. So plastics are about the same density as oil. So in that sense, their low density isn't so much of a problem. And we could put them back in the holes that we made to take out the coal. So we could refill coal mines, for example. My idea is that we actually look after the buried plastic. So we bury all the polyethylene together, and we bury all the PET together, so we know where it is. Because for future generations, it actually represents a highly refined carbon feedstock. So when I say making new fossils, I actually do mean making things that future generations can use. I think one of the things we will have to come to terms with is that we need plastic. If we're going to do it this way, we need it to be very stable. And the reason that geology has done so well in sequestering carbon is that it's turned labile carbon, carbohydrate, into a form of carbon that has been both that has essentially been dehydrated, so it's had hydrogen and oxygen taken out to just leave the alkane behind. And again, I think that the thing that we need to rebury is the alkane, and polymers are essentially big alkanes.
Okay, thank you, Tony. There is a question from a question from Michele Laus, a colleague of us. He said he cannot talk because his voice is too low, and he said, "Hi, Tony, wonderful lecture. I agree that being a professor of plastics is a very hard work. Do you think that also further developments in carbon dioxide chemistry, such as reactions with epoxies to form cyclic carbonates, could represent an effective tool to sequester and use carbon dioxide, or just a little help, a little benefit?"
Sure. So Michele, thank you for the question. So yeah, you can get epoxies from biomass quite easily. So you can use that route. They will react with carbon dioxide to make cyclic carbonates that you can then polymerize. And you can use cyclic carbonates to make all sorts of really interesting molecules. So for example, they can be a feedstock for the kinds of surfactants that are used in soap and shampoo and house cleaning. The advantage that they confer is that they are biodegradable. and there will be some niche applications for the polymers that we could make from cyclic carbonates, because there are some polymers you'd never want to collect, you know, dentures, for example, catheters from the hospital. So there are some things we want to biodegrade, and there is absolutely a niche for that chemistry. And so, yes, it helps a little, and it helps by occupying a niche with chemistry that has low carbon intensity.
Okay, thank you, Tony. Too many technical issues, so I think we have to a little bit change the level. I mean,
yeah, sure.
What is a general question about British, the political ideas of about carbon capture in Britain. So, is there is the country sensitive enough, or let's say the politicians sensitive enough to goes in this direction? Or perhaps it's just sort of, let's say, sort of way to fulfill a request from nowadays. You are not more in Europe, so there are no more requests from Europe. I mean, from United Nations, let's say.
So if we put the political suicide of Brexit apart, the UK government is very well committed to a low carbon future, and has made many investments in this area. The UK is very lucky in its geography for renewable energy, because we have much wind. So there's the capacity for the UK to be a net energy exporter. Even if we electrify all of our heat, all of the gas, that we have enough capacity to make wind energy for all of the UK's economic activity. And if we do that, then we will be leaders in that area and leaders in that technological area. And I think the UK government sees green industry as actually being something that the UK can offer some leadership for, and will be our economic future. So, and that's been a long time coming. It's not just the current government, it's been previous governments that have made those investments possible. So I think the UK is seriously committed to the Paris Climate Change Agreement. What we need to make sure of is that when we go to the new normal post-COVID, that the new normal isn't like it was before. So, for example, I absolutely intend to travel less. I won't get back on aeroplanes because, well, I might have to get on an aeroplane to come skiing in the Dolomiti. But apart from that, you know, it will be a very occasional luxury. It won't be part of my everyday life, which it was before. Similarly, I won't travel as much in the UK, because this is a very efficient way for me to talk to 400 people, because in 20 minutes I'll be dressed in lycra and on my bicycle.
Right. It's I completely agree with this view, but never forget that the work talking in front of people is a different thing.
No, and you know, I would love to be with you.
Yeah.
You know that.
Yeah, absolutely. Yeah.
You know, I really enjoy the company of people from other cultures. It's really important that we share each other's culture.
Yeah, definitely.
So yeah.
Definitely, yes.
We have to work out how to do it without burning fossil fuels.
Yeah, that's correct. That's correct. Anyway, is there any other curiosity? Okay, then. I think that all of us, I just expressed the feeling of all of us to thank again Professor Tony Ryan for his really effective, beautiful, stimulating lecture. And really hope, as I said at the beginning, that our countries, well, of course, our center will continue to collaborate, will start to continue to collaborate, but our countries still be together, still be connected. So this is my really hope, and what we do as a university, what we do is go in this direction, demonstrated that we are unique, we are together just to afford to tackle such a complexity of our future, the complexity of reducing the pollution and greenhouse effect, or perhaps all this the impact of our lifestyle in the environment. So all these are too complex issues to be tackled by a single country. So for this reason, I believe that we are forced to stay together, and so okay, and so but then we'll start to be to collaborate, just to go in this direction. Thank you, Tony, again, and adesso tanti saluti a tutti, grazie a tutti, un caloroso augurio, eccolo lì il nostro Babbo Natale inglese abbiamo, tanti auguri a tutti quanti, e come sapete purtroppo quest'anno non possiamo alla fine della nostra Christmas lecture stare insieme per brindare alle festività che stanno arrivando, ma come sapete siamo tutti insieme nella speranza che il prossimo anno e presto ritorneremo a godere della presenza di ciascuno di noi. Grazie Tony di nuovo, e tanti saluti a voi e alle vostre famiglie.
And now Christmas can start.
Okay, yes, please. Ciao Tony.
Bye.
Bye bye.
Bye bye, auguri.